Professor David Jones. He runs the Neurology AI program, and we'll hear about that program.
Thank you very much. It's a real pleasure to speak with you all. I'm a behavioral neurologist, which I specialize in Alzheimer's disease and related dementias, and my scientific background is in quantitative neuroimaging, turning images into numbers. And I just wanted to kind of take you through the journey of the Neuro AI program, of how we've built this ecosystem, which I think is building what I call the information revolution 2.0 in clinical neurology. And the whole point of this talk, I'll go through at the beginning. Hopefully by the end you'll understand what I'm saying here, but this is the point of the talk. Some of the issues I've seen along the way is that we keep throwing what I would call information 1.0 solutions at information 2.0 problems, while we're writing roadmaps for these 3.0 skyline, which doesn't have foundations. Hopefully that'll be clear at the end. And I think focusing on individual products or project ideas without simultaneously thinking about an evolving, adaptive, interdependent, multimodal, multidisciplinary ecosystem is a sign of 1.0 thinking. But if we want to get to transformation, we're going to have to do 2.0 thinking. And these solutions should synergize and interdigitate new initiatives with organically evolving ecosystems. This is a picture of my desk in 2016. And I'm trying to do patient-centered research, their brain images and precision phenotype. And I love doing this. But there's no way I was ever going to bring this work to my office, to clinical practice. It was never going to happen. And I would sit there and look at images of my patients and look at them and think, if only I could run my MATLAB code on this. That's never going to happen, was never going to happen. But then this happened. Bold forward, this bold idea to be the drivers of transformation. Not let others do it for us, but Mayo Clinic as an organization do this transformation using AI and other technologies. And I said, maybe I will be able to finally bring these sorts of algorithms to my office. And so when I started the Neuro AI program, I thought about how could we do that? And back in 2019, this is a rough diagram of the platform and how I might model data and practice, bring new cures. I said, this is what we're going to do. And then we built a team to do it. And actually, we're actually doing it. This is what it looks like now in 2016. So I kind of want to take you through how we did that. So the Neuro AI program, we believe the best way to get this done was to a multidisciplinary team embedded within the neurology department, where domain expertise, data science, and information technology can all be combined. We speak the same language, a small team, domain experts, data scientists, information technologists. With the little dot in the center of that brain, that's patients. We're always focused on the same goal. That really drives technical decisions when you're focused on this same goal. I've been reading this book lately by General Stanley McChrystal, talking about how he had to reorganize our military to be more successful in the modern age. And he developed these new rules of engagement for a complex world. Surprisingly, it reflects a lot of the way we've organized our team. And I think this is a good way to organize teams of teams. But the vision for our program is to transform neurologic care using high-quality, affordable, widely accessible care models through validated and compliant institutional and departmental technology platforms. So our goals for doing that are to develop these teams to come up with some impactful AI projects that help us build this ecosystem, the infrastructure. We're thinking about the ecosystem the whole time, get the modern data platform, but mainly to build this neurology technology development ecosystem and transform healthcare. So this is neurologists, neuropsychologists, research coordinators, our data science efforts led by Leland Barnard, our software engineering led by John Stricker, postdocs, fellows, administrators. We all speak the same language. We all know where we're going. We're trying to build this NetD to change patient care. And so what could we do with such an ecosystem? So this is a common question. This is a brain FDG PET scan. It shows the metabolism or the energy use in a patient's brain and where it may not be working. common question people ask is, what does this mean? My patients, this is the way their brain's functioning. Does this mean they have dementia with Lewy bodies? Maybe they have some other form of dementia. How we answer this question now is you ask somebody like me, and I say, well, I've seen a brain scan that looks like that before, and that patient did have Lewy body disease. And that's how you extract intelligence from me. You ask me those questions, I think about patients I've seen. And so then to help our residents and fellows, this is our workroom, we paste some examples on the wall. We say, well, look at those. Maybe that'll help you figure out what's going on with your patient. What we've done is digitize this process, and I'll tell you more about that. We're digitizing intelligent work. And I always think about Boltzmann and thermodynamics, and there's this interesting Boltzmann brains, where human brains may be more likely to arise from random fluctuations, which is a reductum ad absurdum argument against purely statistical view of second-order thermodynamics, not important. It was defended by the existence of low entropy at initial conditions, but nobody knows why that fact is true. But what I really care about Boltzmann brains is it has a hidden insight on the gaps between understanding physical descriptions and a scientific understanding of mental world or intelligent work. I've been fascinated by this. Here's an equation. When I first saw equations like this in my thermodynamics courses, I thought it was amazing. Look at that W. That W stands for work. How do we have a mathematical framework for a concept like work? I still cannot get over this fact. This is automation of mechanical work. Thermodynamics helps you do that. When I was at a conference about a decade ago, Brain Connectivity Conference in Vienna, I was landing in the plane and I said, I think Boltzmann is here. Boltzmann's grave is here. And I needed to go take a pilgrimage. I'd recommend anyone go. It's a beautiful cemetery. And life goals, life aspirations, he has an equation there for entropy, on his gravestone. So I think so much about these things. And I think this is important to think about this because the future of what we're trying to do is build a new science is what we need. A science, the future that's coming will describe intelligent work in humans and in machines and power a revolution that automates intelligent work. That's what we're trying to do. So I think Neuro AI and dementia is going to be key to this emerging science. And so we're talking about automation. The Industrial Revolution was automation of mechanical work. Thermodynamics was important for that. How do we regulate that in medicine? Medical devices, software in medical devices are regulated like medical devices. Then the information revolution, I call that the Info 1.0 revolution. This is digitizing perception action cycles, finally getting virtual. That's regulated, information theory, Shannon information theory, software as medical device 1.0. That's how we regulate that now. The problems we're having is with the information revolution 2.0, we don't have the theory. I think that theory is going to be functional infodynamics. The medical equivalent there is not hardware or locked algorithms. It's adaptive ecosystems like NetD. And the regulatory environment, I call it SAMD 2.0, doesn't exist. Information revolution 3.0, where we all think we're going, we got to do 2.0 first. That's where you're doing intelligence, reasoning, simulations. There's no way to get there yet. You need the 2.0 foundation. How do we regulate that now? Human in the loop, clinical decision support systems. We've built a clinical decision support system, and I'll tell you about it. And it's regulated using SAMD 1.0 strategies combined with clinical decision support. So this is a model of biological intelligence that we're working on in the program. Not going to go through that in detail. But it is reflected in our clinical model of brain metabolism. This is deployed in practice on an investigational basis across the enterprise and the Mayo Health System. Every dot that you see in that diagram is a patient's brain. And if they're closer to another patient's brain, that means they're similar. And so you can see there about 10 different classes, all readily differentiable. And so this is Information 2.0 revolution in neurology. It's supported by cloud-based innovation, IT, and data science. And so once again, thinking about functional infodynamics, machine intelligence needs power. We're talking about building nuclear power plants to power data centers to do all this AI work. Human intelligence is powered entirely differently. primarily by mitochondria, primarily by glucose in the brain, 25% of the energy budget. We have directly related the energy use in the brain to functional connectivity, and we're figuring out how these things are related through neurogeneration. Dementia carves the mind at its joints and telling us how it's organized. And so we want to turn this into this, and we did. So what we've done is we developed this program called State Viewer. It's a clinical decision support application that leverages AI and ML technology to improve diagnostic accuracy and efficiency. Makes you 3 to 5 times more accurate. It can do 14 different diagnoses now. Reduces reading time by 50%. It's automated error detection and reporting, static and dynamic reporting. It's only been deployed for about 4 months, but almost 1,200 scans, clinical scans, have been run automatically since that time. It's been ordered by clinicians 103 times. There's been about 1,000 logons to our web applications, and people use that for an average of about 9 minutes. Here is a video of the web application, how you can interact with this data. And so that's the patient's data in the center. Those are the matching cases in our database. And you can explore the data there, brain surface projections. This patient has alexia without agraphia. They cannot read, but they can still write. And here are several other patients in our database who also had that same exact problem. And so not only do we know what the brains look like of these other patients, who looks just like the patient that I'm seeing, we know a lot about what happened to them. Maybe they died and we have autopsy information. We know what drugs may have worked on them. So this is the beginning of the revolution, I think, what an ecosystem of connected data can do for you. And so this FDG PET provides supportive evidence across the entire Alzheimer's disease and related dementia spectrum. And this is what I tell my residents and fellows. You need to make these decisions to get to precision medicine. With one test, we can tell you about 14 different phenotypes right now. Some of these patients need to go to surgery. It's a completely reversible problem of their cognitive issue. And I know all over the world today, those patients are not being treated. We need to treat the treatable things now, and we're not doing that. So we need to scale Mayo Clinic's knowledge. We can do this not just with PET scans, but any other data. We're working on this with digital cognitive testing, at-home speech analysis. And so the same technology that we use to integrate that with current clinical IT, or 1.0, this is just a normal workflow, how you can order these things. It gets to Mayo Clinic Cloud, the NAPE database there. We can do some analysis and get it back in the medical record. This is injecting the information 2.0 revolution inside of existing information 1.0 infrastructure. The same thing is happening with code. So this is a recent lecture by the former head of AI for Tesla, talking about how software is changing again. Software 1.0 is, if-then C+ coding. Information 2.0 is deep neural networks. It's weights. And then information 3.0 is coming, and that's prompts for LLMs. So this is happening quickly. So these are the products that we've built that we call at NetD. We call it the Neurology Digital Ecosystem. It's a cloud-based technology platform using Mayo Clinic Cloud for storage, departmental data, building models, compute, connecting with the State Viewer. State Viewer then is how we connect back to clinical practice and get all these models back in our offices. State Viewer FDG is a Class 2 software as a medical device, analytics, brain like mine, and the whole thing is NetD. We'll be able to put any sort of data through the same platform. So I can tell you a little bit more about intelligence and how that's built into our design and how that's going to be important for regulation in the future. And really, I think we need to change the way we think about regulation and take into the process our understanding of intelligence. But I'll go into more of that some other time. This shows you how the tool can improve your ability and bring it up to expert level. Readers 1, 2, 3, and 4 have different skill levels for reading brain PET scans, but Reader 4 is a trainee. But if you give them our technology, everybody becomes an expert. We're scaling knowledge. And so this is what one of my colleagues recently said. And he said, FDG PET with state viewer is a game changer in practice and very practical for cases in the community. This sort of knowledge sharing and expertise helps us set us apart for patient care. With state viewer, I no longer need to bug, I say that's an error because he does not bug me to help read these scans. It's like having an expert with you in each case. So this is our model. We can do other stuff with that data, model it in other interesting ways, which I won't review today, running out of time. And we can actually take what we know to electrophysiology, because we have the neurology digital ecosystem. There's 100,000 EEGs there. I can now relate all that to brain metabolism in this clinically deployed model. So hopefully this makes a little bit more sense, why I think we're throwing info 1.0 hammers at 2.0 problems, or we're thinking about 3.0 skyline. We need to focus on ecosystems and how we integrate with those. So thank you for your attention. I'd just like to say, we have this small ember of success for engineering intelligence, but there's no guarantee that it's going to continue. It could very well go out. This flame we've built could go out. It needs fuel. It needs more support, and I think we can scale it. But thank you very much.